All right, so example one, represent the spring mass system with a system of differential equations. So this is going to be a system a lot like the one we've seen in section 3.6, but the main difference between this system and that system is that instead of having one spring and one mass, we're actually going to have two springs and two masses. And let's just say each mass has mass M1 and M2 for box 1 and box 2. Springs 1 and 2 have spring constants K1 and K2. And let's say equilibrium for this first box is about here. And for this second box, let's just say it's here. So we can represent the displacement of this box away from its equilibrium position with a function. Let's call this one x of t and this one y of t. And this really just is measuring towards whatever point you have here that lines up with the equilibrium position. And so what we're going to be doing before we want to, so what we need to do to find the system of differential equations is to plug this into Newton's second law. Force equals mass times acceleration. So right now we have mass. We can easily get acceleration because just the second derivative of these position functions. But finding the force is going to be a little bit more difficult. And how we're going to go about doing that is by creating free body diagrams. And if you've taken physics or you're in physics, you know what that is. But just in case, a free body diagram is pretty much just a simple way of representing the forces that are being applied to just an object. So you can see for mass 1, it has a force this way from this first spring and a force this way from this second spring. And so finding the force on the left is pretty simple because it's just this spring constant times whatever the displacement is. So it's going to be K1x. And then finding the second force on the right, it's a little bit more complicated. It comes out to be K2 times y minus x. And the reason for this is because although you're trying to figure out the displacement of this box to find out how much it's stretching or this spring is pulling on mass 1, the force applied actually also depends on the position of mass 1, because if you imagine mass 2 is pulled really far this way, the force actually could be 0 if mass 1 is pulled the same distance that way. So this spring is completely in equilibrium, whereas this spring is where all the force is. And so we're going to do the same thing for mass 2. And so we know that springs pull with the same amount of force on both sides. So if we have spring 2 applying this much force, K2 times this quantity, to mass 1, we know it also applies the same force to mass 2. So we're going to put in K2 times the quantity of y minus x. Oh, I forgot to label that there's also a force, F of t here, pulling on the end. And that's just going to be our force for the right-hand side of mass 2. And so now that we have all the forces, we can start plugging this into Newton's second law. So for our first equation, we're going to have mx double prime for mass 1. Oh, m1 x double prime, my bad. And that's going to be equal to the sum of the forces. And so when we're summing the forces, just make sure that opposite forces go in, they have different signs. So if this one's positive, this is going to be negative. That's just so the math knows it's in different directions. So when we plug it in, we're going to get m sub 1 x double prime equals negative k1x plus k2 times the quantity of y minus x. And then for the second mass, we're going to get negative k2 times the quantity of y minus x plus f of t. And there is our system of differential equations representing this system.